All right, welcome back to Talk Tensors. Today we're taking a deep dive into something that really caught my eye. This paper called Impula, The Power of Average Pooling for Image-Based Deep Reinforcement Learning. And I know that title might sound like, well, a mouthful, but trust me, this paper gets at a really fundamental question about how we build visual systems for AI. How do we let these AIs actually see and understand the world?
It's true, that title does sound pretty dense, but you're right, this paper is surprisingly elegant in the way it approaches this problem.
Exactly. And the implications, well, they could be pretty significant, especially when you start thinking about things like robots that need to navigate the real world and make decisions based on what they're seeing. But I'm getting ahead of myself. Why don't we start with the basics, just to make sure everyone's on the same page. For a long time in machine learning, the thinking, especially when it comes to images, has been that bigger is better. More parameters in the model, more layers, all that. It should lead to better performance.
Yeah, that's been the general trend. We've seen it in image classification, natural language processing, pretty much across the board. And the intuition there, I think, is pretty straightforward. If you have a more complex model, it should be able to capture more complex patterns in the data, right?
Right. So when we started applying deep learning to reinforcement learning, particularly for tasks that involve visual input, like a robot navigating a room or an AI playing a video game, the initial thought was, well, let's just scale up the size of these visual encoders, these neural networks that process the images, give more layers, more neurons, more parameters, and they should be able to learn more intricate details and understand the visual world better, right?
Exactly. And that approach did lead to some significant progress. We saw architectures like ImpalaCNN, which is a fairly large convolutional neural network, become pretty popular in image-based deep reinforcement learning. It showed some real improvements over earlier, simpler designs.
So everything was going great, bigger models, better performance, everyone's happy, right? But then this paper comes along and asks a really interesting question. Are we so focused on just making these visual encoders bigger and bigger that we might be missing out on some crucial performance gains that could come from smarter, more efficient architectural choices, specifically tailored for the unique demands of reinforcement learning? We're hitting a point where just adding more parameters isn't giving us the same kind of returns we're used to seeing in other areas of machine learning, like image classification.
Yeah, it's like, are we just blindly following the same scaling rules that worked before, or is there something unique about deep reinforcement learning, especially when we're dealing with visual input, that might require us to rethink how we design these networks from the ground up? And this paper makes a pretty compelling case for the latter.
And their key finding is honestly pretty surprising. They found that by making what seems like a really small change to this ImpalaCNN architecture, they were able to get a significant boost in performance, particularly in how well these AI agents could adapt to new and unfamiliar situations.
And the change they made is, well, it's almost deceptively simple. They just swapped out the final flattening layer in ImpalaCNN for something called global average pooling.
Right. Now, I know to anyone who's not super familiar with the nitty-gritty of neural network architecture, that might sound like some, arcane technical jargon. But trust me, the concept itself is actually pretty intuitive, and the implications, well, they're quite profound.
Yeah, maybe we should take a step back and explain what this flattening layer and global average pooling are all about.
Yeah, good idea. So imagine you have this convolutional neural network like ImpalaCNN processing an image. It's doing its thing, extracting features, learning patterns, and all that. And at some point, you end up with these feature maps, these spatial representations of the image that capture different aspects of what the network is seeing. Now, in the original ImpalaCNN, the next step was to take all these feature maps and, well, flatten them. You basically just stretch them out into one long high-dimensional vector.
Yeah.
It's like taking a bunch of 2D pictures and turning them into one really, really long strip of pixels.
Right. And then this very high dimensional vector is fed into the final fully connected layers of the network, where it's used to make decisions like, what action should the AI agent take next? But what the authors of this paper found is that this flattening process might be causing some problems.
Yeah, they noticed that a surprisingly large number of the neurons in the linear layer, the layer that comes right after this flattening operation, were essentially dormant. They weren't really activating much during the training process. And they point out that this layer, because it's taking in this super high dimensional vector, actually contains the vast majority of the network's parameters. So you have this massive layer, over 80% of the network's weights are concentrated there. And a significant portion of it is just sitting there, not really doing much.
And that's pretty inefficient, right? You're using all this computational power, all these parameters, but a lot of them aren't really contributing to the learning process. Now, someone might say, well, if those neurons aren't firing, why not just prune them out? Just get rid of the inactive weights. And yeah, pruning is definitely a technique that people use to make neural networks more efficient. But the authors argue that the core issue here isn't just the inactive neurons, it's the flattening operation itself.
They hypothesized that this flattening process, by creating this super high-dimensional embedding space, might be contributing to training instabilities. It's like you're taking this rich spatial information from those feature maps and just squashing it all into this one huge tangled mess of vector. And they think that this might make it harder for the network to learn features that are actually useful for generalization, for adapting to new and unfamiliar situations.
Yeah, it's like you're forcing the network to learn in this really complex interconnected space where it's easy to get lost in the details and miss the forest for the trees.
And their solution is this global average pooling, or GAP. Now, instead of flattening those feature maps, GAP essentially calculates the average value across all the spatial locations within each feature map. So it's like taking each feature map, which is like a little map of what the network is seeing, and summarizing its overall activation level with a single number.
Yeah, it's like saying, okay, this feature map is really active, so it's probably detecting something important. Let's represent that importance with a high average value. And this other feature map is mostly quiet, so its average value will be lower. And by doing this for each feature map, you end up with a much lower dimensional representation that gets fed into the final layers.
Exactly. So to go back to our example, if you have, say, 64 feature maps that are 8 by 8 in size after the convolutional processing, flattening would give you a vector that's 4096 dimensions long. But with GAP, you're reducing that down to just 64 values. And that's a massive difference in terms of the number of connections and parameters in the subsequent layers.
And that reduction in complexity, well, it seems to have some really significant benefits.
Absolutely. They tested this modified architecture, which they've cleverly named Impula CNN, on the Procgen Benchmark. And for those who aren't familiar, the Procgen Benchmark is a set of procedurally generated game environments that's specifically designed to test how well a deep reinforcement learning agent can generalize to new and unfamiliar situations. So it's a really good way to see how well an AI can adapt to changing circumstances, which is, kind of crucial for real-world applications.
And the results were pretty remarkable. Impula CNN consistently outperformed the original ImpalaCNN on this benchmark.
Yeah, they saw some pretty significant improvements. In some cases, they got up to a 17% increase in their IQM metric, which is a measure they use to quantify the overall performance and consistency of the agent across all these different game environments. And they achieved this while using up to 35% fewer parameters than the standard ImpalaCNN. So not only is it performing better, it's also more efficient.
Which really challenges this assumption that just making our models bigger and bigger is always the best way to improve performance, especially in deep reinforcement learning. It suggests that maybe we should be paying more attention to these architectural choices, these seemingly small tweaks that can have a surprisingly large impact.
Right. And it's not just about the overall performance either. The paper also delves into some of the specific reasons why this global average pooling seems to be so beneficial. One key aspect they highlight is the impact on something called translation sensitivity.
Yeah, so translation sensitivity refers to how much the output of a neural network changes when the input image is shifted or moved slightly. Ideally, for a lot of computer vision tasks, we want our networks to be somewhat translation invariant. We want them to be able to recognize an object regardless of its exact position in the image. Like, if you show a network a picture of a cat, it should be able to recognize it as a cat, whether it's in the center of the image, off to the side, or partially obscured by something else.
Right. It shouldn't matter where in the image the cat is. The network should still be able to identify it. And global average pooling, well, it inherently helps with this because it's pooling information across the entire spatial extent of each feature map. So it's not as reliant on the precise location of specific features. It's more about capturing the overall presence or absence of those features, regardless of where they happen to be in the image.
And their experiments showed that ImpalaCNN was indeed less sensitive to these shifts in the input image compared to ImpalaCNN. And they suggest that this reduced sensitivity might be a key factor contributing to its improved generalization performance, especially in these game environments where the AI agent's position within the scene is constantly changing. It's like if the network is less sensitive to these small positional changes, it's better able to focus on the more abstract, high-level features that are actually important for understanding what's going on and making decisions regardless of the agent's exact viewpoint.
They also did some interesting ablation studies where they tried replacing that flattening layer with other common pooling techniques. So instead of global average pooling, they tried things like taking the average value in small local regions of the feature map, like a 2x2 grid, or taking the maximum value in those regions. But none of these other techniques provided the same level of generalization benefits as global average pooling.
Which further supports their argument that there's something special about this global average pooling that makes it particularly well suited for deep reinforcement learning with visual input. It seems to strike a good balance between retaining enough spatial information to understand the scene while also promoting this translation invariance that's so important for generalization.
Right. Though they did notice an interesting detail. In games where the agent's viewpoint was fixed at the center of the screen, the original ImpalaCNN actually showed some initial advantages.
Yeah, that was a bit curious. And they speculate that this might be because in those agent-centered games, having more precise positional information is actually helpful, at least early on in the learning process. If you know exactly where things are in relation to the agent, it might make it easier to learn some basic behaviors. But they also found that this initial advantage faded away as the tasks became more challenging, with ImpulaCNN eventually surpassing ImpalaCNN even in those agent-centered games.
Right. So it seems like having that precise positional information can be helpful in some very specific scenarios, but it can also lead to overfitting. The network might become too reliant on those exact pixel locations and struggle to generalize when things are presented in slightly different ways. ImpalaCNN, on the other hand, by being less sensitive to these exact locations, seems to learn more robust, more abstract features that are better suited for handling a wider range of situations.
Yeah, it's like the difference between memorizing specific examples and actually understanding the underlying concepts.
Exactly. Now, they also revisited that dormant neuron observation we talked about earlier, but this time they looked at an earlier layer in the network, the second convolutional layer. And what they found was quite interesting. In ImpalaCNN, the number of dormant neurons in this earlier layer actually increased during training. But in ImpalaCNN, that didn't happen.
That's pretty intriguing. And they suggest that this might be because of the more balanced distribution of network weights in ImpalaCNN. By using global average pooling, they're essentially reducing the dominance of that final linear layer, which, as we mentioned, was hogging most of the parameters in ImpalaCNN. And this more balanced distribution seems to lead to a smoother and more stable learning process throughout the network. It's like by spreading the workload more evenly, they're preventing any one layer from becoming a bottleneck and hindering the overall learning process.
Okay, so we've talked a lot about the specifics of this ImpalaCNN architecture and the experiments they ran, but to really appreciate the significance of this work, I think it's helpful to step back and look at the broader historical context. How we've been approaching visual processing in deep reinforcement learning over the years. The paper itself does a good job of this, referencing earlier architectures like the Nature CNN, which was kind of a foundational image encoder for DRL, and how ImpalaCNN built upon that foundation to achieve significant progress.
Yeah, it's a good reminder that our understanding of the right building blocks for these systems has been constantly evolving. And it's not just about blindly following what worked in other areas of deep learning, like image classification. There are unique challenges and considerations that come into play when we're dealing with the dynamic nature of reinforcement learning environments and the need for generalization.
The paper also highlights a key difference between deep reinforcement learning and supervised learning, particularly in the context of these scaling laws we've been talking about. In supervised learning, like image classification, we've seen these fairly clear scaling laws where, generally speaking, adding more layers or parameters often leads to better performance. But in DRL, it's not always that straightforward.
Yeah, it's not just a matter of bigger is always better. There are other factors at play, like the complexity of the environment, the types of tasks the agent needs to perform, and the specific goals of the learning process. And those factors can influence how well different architectures scale and generalize.
And it's interesting to see how much attention network scaling in DRL has been getting lately. The paper cites a bunch of recent studies exploring different approaches to this, from adjusting the width of layers to pruning unnecessary connections to introducing more complex computational units, like these mixture of experts models. It really feels like the community is actively grappling with this question of how to build more capable and efficient DRL agents.
Yeah, there's definitely a growing recognition that simply making our networks bigger and bigger isn't a universal solution. We need to be smarter about how we design these systems, considering both the performance and the efficiency aspects. And this ImpalaCNN paper really adds to that conversation by emphasizing the importance of the underlying architectural choices we make.
They also touch on this concept of translation invariance, which we talked about earlier, and how global average pooling has been used in other areas of computer vision to promote this property. They cite some important foundational work in that area, and it's a good reminder that these ideas often have a rich history and can be applied in unexpected ways.
Yeah, it's like standing on the shoulders of giants, right? We can build upon these fundamental insights and adapt them to new and challenging problems.
And, of course, we can't talk about generalization without mentioning the Procgen Benchmark itself. It's a really valuable tool for evaluating the robustness and adaptability of DRL agents, and it's great to see it being used to rigorously test these new architectural ideas.
Absolutely. And the fact that Impula CNN performed so well on this benchmark, especially compared to the larger Impala CNN, really speaks to the effectiveness of this architectural approach. It suggests that global average pooling might be a key ingredient for building DRL agents that can truly generalize to new and unfamiliar situations.
Okay, so just to recap the key takeaways from this paper, the core innovation here is that seemingly simple swap of the flattening layer for global average pooling in the Impala CNN architecture. And this leads to a number of benefits, including a more balanced distribution of network weights, significantly improved generalization performance, and even a reduction in the number of parameters needed. And the mechanism behind these improvements seems to be tied to this reduction in translation sensitivity, allowing the network to learn more robust and abstract features that are less reliant on the precise location of objects in the image.
Yeah, and the broader message here, I think, is that we shouldn't underestimate the power of thoughtful architectural design in deep reinforcement learning. It's not just about throwing more parameters at the problem, it's about finding the right building blocks and arranging them in a way that promotes efficient and effective learning, particularly when we're dealing with the complex and dynamic nature of visual input.
Right. Now, this paper primarily focuses on simulated game environments. But it's not hard to see the potential real-world implications of this kind of research. They briefly mention some areas where this could be particularly relevant, like robotics, automated driving systems, and robotic locomotion.
Yeah, imagine a robot that needs to operate in a real-world environment where things are constantly changing and unpredictable. Objects might be in slightly different positions than they were during training. The lighting might be different. There might be clutter or obstacles that weren't there before. If that robot's visual system is overly sensitive to those small changes, it might struggle to adapt and make the right decisions.
And that's where an architecture like Impula CNN, with its reduced translation sensitivity, could really shine. It could allow robots to be more robust and adaptable in those real-world scenarios. Like an autonomous vehicle that can still recognize pedestrians even if they're partially obscured by other cars or trees, or a robotic arm in a factory that can still grasp objects accurately even if they're not perfectly positioned.
Exactly. And beyond robotics, this principle of prioritizing efficient design over just brute force scaling could have implications for other areas of deep learning as well. Anywhere where we're dealing with limited computational resources or where generalization is a major challenge.
Right. Okay, so that brings us to our novel notions segment, where we like to take a step back and, based on the paper we've discussed, brainstorm some potential research directions that could be interesting to explore. And I've got a couple of ideas that came to mind while reading this paper.
I'm all ears. Let's hear them.
Okay, so the first one is inspired by their discussion of translation sensitivity. What if, instead of just reducing translation sensitivity across the board, we could develop mechanisms that allow the network to dynamically adjust its sensitivity based on the complexity of the visual environment?
That's an interesting thought. You're saying, like, if the environment is really simple with just a few objects and a clear background, maybe it's beneficial to retain more precise spatial information. But if the environment is really cluttered and complex with lots of objects and visual noise, then maybe it's better to shift towards a more global, less position-dependent representation.
Exactly. You can imagine a network that analyzes the incoming visual data, and based on some measure of complexity, like the entropy of the image, or maybe even the agent's own uncertainty about its current state, it decides how much emphasis to put on precise positional information versus more abstract global features. It's like having an adjustable focus lens for the AI's vision, where it can zoom in on the details when needed, or zoom out to get a broader view when the scene is too chaotic.
I like that analogy. And this could potentially build upon existing research in areas like adaptive computation and attention mechanisms within neural networks. Those fields have already made some progress in developing networks that can dynamically allocate computational resources or focus on specific parts of the input based on the task at hand. So maybe we could adapt those techniques to this problem of dynamically adjusting translation sensitivity.
Right. And this could lead to some really interesting advancements in terms of building more versatile and efficient DRL agents that can handle a wider range of visual environments. They could seamlessly transition from simple, clean, simulated worlds to messy, unpredictable real-world scenarios.
Yeah, that would be a huge step towards more robust and adaptable AI systems.
Yeah.
Okay, so that was your first novel notion. What's your second one?
Right. So the second one is kind of a counterpoint to this idea of reducing translation sensitivity. And it's inspired by their observation that ImpalaCNN, with its higher sensitivity to position, actually performed better initially in those agent-centered games. So what if, instead of always striving for complete translation invariance, we could develop techniques that allow us to control and exploit a certain degree of sensitivity to specific types of transformations?
So you're saying that maybe in some tasks, it's actually beneficial for the network to be sensitive to how its actions affect the position or orientation of objects in the visual scene. Like if you're trying to learn how to grasp an object, knowing exactly how your movements are changing the object's position in your field of view might be really important.
Exactly. And maybe we could design networks that have a kind of tunable knob for translation sensitivity where we can dial it up or down depending on the task. Or maybe we could even design specialized DRL agents for different classes of problems, each with a carefully calibrated level of sensitivity to specific types of transformations.
I see what you're getting at. It's like instead of always trying to eliminate sensitivity to transformations, maybe we can learn to exploit it in a controlled way to improve performance on certain tasks. And this could be particularly relevant for things like robotic manipulation, where precise control over movements and understanding how those movements affect the visual scene is crucial.
Right. It could even lead to some interesting connections with research in areas like computer graphics and physics simulation, where people have developed sophisticated techniques for modeling how objects move and interact in virtual environments. Maybe we could borrow some of those ideas and incorporate them into our deep reinforcement learning systems.
Yeah, there could be some really fruitful cross-pollination there. And it just goes to show that even a seemingly straightforward concept like translation sensitivity can lead to some really rich and unexpected research directions. It's all about understanding the nuances of how these architectural choices affect the learning process and finding the right balance for the task at hand.
Okay, so to wrap up our deep dive into Impula, this paper has really highlighted the power of efficient network design in deep reinforcement learning. And it's given us a lot to think about in terms of how we approach visual processing in these systems.
Yeah, it's a great reminder that sometimes even seemingly small architectural tweaks can lead to big performance gains and open up exciting new research avenues.
Absolutely. So for those who want to dive into the details, we'll include a link to the paper in the show notes. And as always, thanks for joining us on Talk Tensors. We'll see you next time.